All right. We were doing NP hardness and we were doing reductions. And last time we met, we were doing a reduction from 3 set to vertex cover. Yes. Okay. Cool. Plan for today is to do another reduction from 3 set to 3 colorability. Any questions from the last lecture? The reduction we did last time? All right. The problem. So, दो problems का plan है आज का. I hopefully have enough time to do both of the reductions. The first one is the 3 colorability. I think we have seen this problem at least twice before. Remember, we discussed a problem where we said that you have a list of guests at our wedding, and some of them hate some of the other people in the guest list, and what you have to do is you have to seat them on the minimum number of tables. Okay, so 3 colorability is a problem when you only have 3 tables, and you have to decide whether you can seat everyone on those 3 tables or not. Okay, so it's a decision version of the problem. So your answer is either yes or no, and you get a list of guests, and you also get the kind of hate relation. Okay, so for example, over here A hates B, which means that A and B both cannot be seated on the same table. B hates C, but A and C can be seated on the same table, right? Similarly, A and D can also be seated on the same table. So this graph kind of tells you who can be seated on the same table, which pair can be seated on the same table, and which pair cannot be seated on the same table, right? This graph is 3 colorable, which means that you can see them in the 3 tables. A and D can go on the same table. Oh, I see a problem. So B and E should not be seated on the same table. Hai na? The color is wrong. Let's figure out if we can actually do 3 colorability of this graph. I can put F and B on the same table and E and C on the same table, right? So assume that B is colored green and C is colored purple. Then this graph is valid. Okay? So this graph is 3 colorable. Everyone understands the problem? Yes, no? Yes? Yes? Okay. So the 5 cycle is 3 colorable. The 3 cycle is 3 colorable. But this graph is not 3 colorable. Maybe we saw this last time as well. But A, B, C, D. This graph is not 3 colorable. You can't color this graph with 3 colors. All right, okay. And our problem today is to prove that we can do this. We can reduce 3 set to 3 colorability. All right, yeah. If the graph is fully connected and the number of nodes are more than 3, then definitely it's not 3 colorable. Yeah. Any K, capital K, small k, where K is more than 3 is no instance. Who is talking? Who is talking? All right, any questions regarding the problem? Okay, so plan is to reduce 3 set to 3 colorability. That will prove that 3 colorability is NP hard. But we also do one more thing when we are trying to prove something is NP complete. What's that? If I want to prove 3 colorability is NP complete, this is one of the things that I have to do. What else do I have to do? You prove that this is also in NP, right? So this would imply that 3 call is in NP hard, and the second step that is required is that 3 call is NP. Can someone quickly do it for me? This part is, I think, somewhat trivial, if I dare say. How do we do this? How do we prove that 3 colorability is in, sorry, NP, not P. NP, non-deterministic polynomial. Do you have an answer? Can anyone tell me the plan? If I want to do this, what is required of me? What would a proof of this statement look like? Yeah?
Like if we have a certificate and we are given an answer that is supposed to be correct, we can go to each vertex, check whether a edge is matching with the same
Right.
and that.
Right. Yeah. So a polynomial size certificate is required to prove that 3 call is in NP, and that certificate could be the coloring of the vertices. Okay? If I tell you the color of each vertex, you can go and verify whether that color is a proper coloring. Okay? Proper coloring means that every pair of adjacent vertices have different colors. Okay? So I can do it in polynomial time, obviously, which means the 3 colorability is in NP. All right. Are we good? Yes, no? Something like this is definitely on your exam. So if it's not clear, now is the time to make noise. Yeah. So I give you a graph, and I ask you whether this is 3 colorable or not, and you say, yes, it's 3 colorable. And then I say, no, I don't believe you. And then you say, no, that's definitely 3 colorable, and here is a proof. Okay? And the thing that you give me as a proof is a certificate, right? And you have to figure out what that is. That's the kind of slightly intellectual part of the game, that you actually figure out what is that I can give to someone, and they can quickly verify that it's true. Okay? So that certificate, and for 3 colorability, the certificate is that you give them the coloring. You tell them, okay, color A, blue, color B, red, and color C, this, right? And then once you give me the coloring, I can definitely look at the graph and verify that each edge receives 2 different colors. Each of the edges non-monochromatic, right? So that's the kind of intellectual part. Are we good? All right, let's move on to the more interesting part, which is proving the 3 set is polynomially reducible to 3 colorability. So this would prove that 3 set and 3 colorability are somewhat equivalent in problems, like we proved for the vertex cover, right? We proved that 3 set and vertex cover are somewhat equivalent in nature, right? But why? I mean, to me, have you seen those reels where they have this small kid and he has never seen anything, he's kind of born blind or limited vision, and they gave him a glasses at some point, and he's totally puzzled. He's not happy or sad or anything, but he's super puzzled, right? To me, this is one of those moments when I say that 3 set, which is that I give you a kind of a formula, a mathematical formula, where you have these variables, literals, AND gates, and NOR gates, and then you check whether it's satisfiable or not. And then I give you this camera setup, and I give you road network, and I ask you whether you can place cameras that can watch all the roads, right? And then I say that these 2 problems are equivalent. They're somewhat same. Solving one problem will solve the other problem for you. I think to me this is extremely amazing statement, surprising statement for me. And that's something similar, right? 3 set is absolutely on surface, it's nothing like 3 colorability. All right, we'll do something similar for another problem, maybe today, and And this is also quite surprising, and that problem will require us to prove that 3 set is reducible to something called subset sum problem, which involves integers. Anyhow, okay, so Polo? Okay, so last time we did an exercise where we said that we have to design an algorithm whose input is what? To do this, we have to, whose input is what? So मैं ये कह रहा हूँ कि इसको करने के लिए I have to design an algorithm, right? और इस algorithm की कुछ input होगी और कुछ output होगी, right? What's going to be the input of this algorithm and what's going to be the output? What's the input of this algorithm? Yeah? Absolutely, absolutely, yes. So this algorithm takes as input instance of 3 set or 3CNF formula, okay? F. And what's the output? Yeah. Bolo?
Instance of 3 coloring.
Yeah, instance of 3 coloring. All right, so it outputs the input of the target problem, instance of free colorability. All right, so our input is this formula which has literals, something similar to what we had last time. A literal has variables and, a Boolean formula has clauses which are ands, which are ORs of literals, and then you get ands of the clauses. So x2 or x3 bar or x4 and I don't know, whatever, x2 bar or x3 bar. Did I not use any? Yeah, I guess these. Okay, something like this, okay? And from this I have to generate a graph, okay? All right. Any crude ideas? How do I generate a graph? So I'm going to have to generate a graph. This graph should be 3 colorable only if the original formula is satisfiable, and this graph should not be 3 colorable if the original formula is not satisfiable. All right, that's the plan. So colors for 3 coloring are just the names for any particular class. Okay, so you can call them blue, red, green, but you can also call them true, false, and something else. Yeah, go ahead.
I guess firstly we could separate the variables themselves into different triangles like in vertex color, where we can assign them different colors, true or false. Like let's say we have x or x naught, either one of them would be true.
Right, definitely. Okay, cool. That's a really good idea. That's a really good idea. So that's the beginning of where we should start. So he says that for each variable we have 2 nodes, and we can connect them by an edge, which means that these 2 nodes cannot receive the same color. Right? Will be whichever coloring we figure out for graph G, x1 and x bar would receive different colors, which is great, right? Okay. So since this is free colorability, we have to force that they either receive the true color or the false color, but not the third color, whatever the third color is. Okay? Okay? So again, I said that you can name the colors yourself. Okay? So and to make things kind of easily understandable, what we do is we name them true, false, and for conventional reason, base. Okay. So if I add this triangle to my graph, these three nodes will receive different colors. These three nodes will receive the three colors जो मेरे पास हैं. Okay. They could be R, G, B, or they could be true, false, and base. So far, so good. So now, how do I make sure that x1 and x bar receive either a true color or a false color? So abhi tak I have made sure that x1 and x bar receive different colors. है ना? If I add an edge between them, that guarantees that both of them will receive different colors. Now I have to make sure that they receive either the true color or the false color, because those are the valid colors for me. क्या?
Make an edge with base क्योंकि फिर
क्या?
it has to be either true.
Absolutely, absolutely. You had the same idea? Yeah. So if I connect x1 to base and x2 to base, then I'm guaranteed that they cannot be colored base. They're either colored true or false. Okay? All right. What next? So far I have done some constructive work on my variables. क्या?
I mean, I have done through some structures for clauses.
Okay, cool. So now I have to figure out a structure for clauses, right? So I can have something similar for every variable. So I will have a similar edge for x2 bar, similarly connected to base, and so on. Okay. So for each variable in my formula, I have two nodes in the graph that I'm constructing, right? Now I have to figure out a way to introduce them to my clauses. Okay. So all right. So each class I am guaranteed that that each class will have exactly 3 literals. Okay. So let's just say those literals are L1, L2, and L3, and let's say this is the clause I. Okay. So Li1, Li2, and Li3. What do I need to make sure? So I need to make sure that my graph is colorable only if every clause in the formula is satisfiable. And for that particular clause, it means that if all 3 literals are false, then my graph should not be colorable. Okay? But if any one of them is true, then it should be colorable. Okay? So that's the plan. So here is a structure that ensures that. So if I connect this to a triangle, this triangle mimics the OR operation in graph terms. Okay, so if both of these literals were false, then this guy is either true, right, or it's base, and this guy is either true or it's base, right? But both of them cannot be the same color, which means that one of them is true and the other one is base. With me so far? Right? So once again, if both of these, I'm assuming both of them are false, okay? There are 4 different cases. This is probably the most crucial case. If both of them are colored false, then this node is colored either true or base, right? Because you cannot have a false there, right? And this node is also colored true or base. But I connect them by an edge, which means that they cannot be the same color. So one of them is true and the other one is base. Yes? Okay, so let's assume that this one is true and this one is base. Okay? What's the color of this node? False. Okay? So I achieved what I was looking for. I am able to, using this triangle, take an OR of these two literals. Okay? Let's just, for sanity check, okay, if one of them is true, then I can receive a true here. So if let's say this is true and this is false, I could receive a true here and I could receive a false here and I could receive a base here. Or I could receive a base here and a true here. Yes? Yeah. Base is the third color. So I'm allowed 3 colors. एक कलर का नाम मैंने true रखा है, एक कलर का नाम मैंने false रखा है, थर्ड कलर का नाम कुछ भी रख सकते हैं आप. You can call it X, you can call it whatever you want, but I'm calling it base because they usually call it base in this construction. All right. So we all agree that this triangle is doing an OR operation. Good. What do I do next? So my ultimate goal was that if one of these is true, then the graph should be colorable. If all 3 of them are false, then the graph should not be 3 colorable. Okay? So I only did OR of 2 literals. What do I do next? Yeah. Huh. Huh. Yeah. Cool. Yeah, absolutely. So what I need to do is I need to take the output of this OR and OR it with the third literal. Yes? Okay. So exactly the same structure. Okay? Are we good? So this is a structure which is a clause in my original graph. अब यहाँ पे if this turns out to be false, my graph should not be colorable. And if this turns out to be true, then the graph should be colorable. Okay? So what do I do? Yeah. Yeah. You just connect. You remember the parallel triangle that you had? So you connect it to the false node in the parallel triangle. So this F is that F right there. So let me just kind of make the same triangle again here. Yeah.
High vertex के colors are not fixed in the K-colorability problem, ना?
They are not fixed.
तो ये जो end में हमने false के साथ edge लगाया है, you could वहाँ पे true भी तो हो सकता है.
Absolutely हो सकता है. Absolutely हो सकता है. So again, a very valid question. Can someone close the door for me? Thank you. So the question is, I'm not guaranteed that this node will receive an F color. I'm not guaranteed that this node will receive a true color, and I'm not guaranteed that this will be B. What I'm guaranteed is that these 3 nodes will receive 3 different colors. Right? So what if this node receives true color that I'm connecting to the node over here? Do you see the problem? Right? So how do we solve this? You have a question? Do you understand his question? Okay. Do you have a follow-up question on that, or a different question? Let's wait for it. Okay. Let's try to resolve this first. So after making this triangle, I'm guaranteed that these three nodes will receive different colors. I'm not guaranteed that they will receive the exact three colors जो मैंने यहाँ पे label किए हैं, है ना? So how do I resolve it? There's a reasonable resolution for this. First of all, everyone who agrees that this is a problem. Okay. Do you have a different question or a resolution for this problem?
Can we just define the colors as one of these colors? For example, if our colors are RGB, we can...
Definitely. So I can define my colors to be T, F, and B. That's fine. So I can guarantee that these three vertices receive three of these colors. But I'm not guaranteed that node I'm connecting to the output of this clause is F. That's not guaranteed, right? How do I fix this? This is fixable. So the question is, by doing this kind of circus, I create a graph, and I say that I give it to the three colorability black box, and I ask it to color it. Okay. While constructing this gadget, I kind of assumed that this node will be colored F. है ना? Because I'm connecting it to the output of this gadget. And if this is F, this cannot be F. And if this cannot be F, तो फिर these three cannot be an F. है ना? If these three cannot be an F, तो फिर original formula satisfiable नहीं है, or this graph should not be colorable. Right? But what if this node turns out to be a different color than F? What if this node turns out to be a color B or a color T? I know that these three nodes will receive three different colors, but what if those three colors are, for example, this is F, and for example, this is T, right? Then is something lost? You have a resolution for this problem?
It's not a complete resolution, but if we have another triangle जिसे हम उससे connect करके, that would force our वो वाली vertex to be on a one color, लेकिन ये नहीं पता कि वो one color है.
Oh, okay. You're trying to resolve the problem by changing the construction or adding something to the construction.
Yes.
There's a way to resolve this construction without changing anything. I think the construction is okay. It's just that we have to argue about it. We have to say that what his argument is not that big of a problem. क्या? Right. Right. But here's the thing. That is based on the assumption that this is an F. है ना? अगर ये F नहीं है, तो फिर this could be, for example, B. Or this could be F. I mean, this could be an F, right? If this is T, then this could be an F, right? But it should not be an F. It should not be allowed to be an F, right? Come on, this is fixable. This is easily fixable. बोलो.
नाम interchangeable है.
हाँ.
तो अगर two है भी, then that just means कि two
हाँ.
का मतलब है कि हमारी original equation में वो
Absolutely. That's the resolution. So देखो, उसका नाम क्या है उससे कोई फर्क नहीं पड़ता. मैंने उसका नाम false रखा हुआ है. Okay? So if you give me a graph, और वो graph 3 colorable है और उसके अंदर you used color for example blue, red, I have to use a different color, green and blue. Okay. This graph is 3 colorable. The actual colors don't matter, right? I could name blue as red, and then I have to change the name of red to what? Blue or green maybe, I don't know. And green to blue, and then blue to red. Okay? So the names of the colors are interchangeable. Okay? If there is a coloring in which this node is colored true, then there is another coloring in which this node is colored F. All I have to do is swap the colors true with false. Okay? सारी true nodes को मैं अगर false कह दूँ और false nodes को true कह दूँ, तो this formula is still colorable. This graph is still colorable. तो actual colors जो इन nodes को मिल रहे हैं, they are insignificant. They don't matter. Okay? All that matters is the graph is colorable. Okay? So that means that I can assume that this node is colored F. Okay? Cool. Okay. Good. You had a question. No, not anymore? Okay, cool. So in the final construction, you construct a similar gadget for every clause. This clause means the literals are coming from here. These are your literals. And you connect the output of each literal to false. If this graph is recolorable, then the original formula must be satisfiable. And if the original formula is satisfiable, then this graph must be colorable. Okay? Convinced, or do you want me to say more? Yeah.
If this is an OR gate, the L2 and L3, then
Okay.
will it always return true?
This will return true whenever one of them is true.
It can also return B.
It could return B, but again, I said the names of color are interchangeable. So it could return B, okay? It could return B, but it could return T. So you're saying when I color it B, then I have a problem. Okay? But what I'm saying is that there are infinite number of, well, not infinite, but there are a lot of bad colorings of this graph. Okay, there are. It's bothering me. How many are there? 3 to the power n. Pretty much 3 to the power n, close to 3 to the power n, incorrect colorings of this graph. But all I need is one correct coloring. And that's what I'm saying is possible. There is one possible way in which if one of them is true, I can make this true, and then I can make this true. And then that's all that matters. Okay? So there is a way to color it incorrectly. You're right. But that's not important. The important is there is a way to make this a good coloring. But if the original formula is not satisfiable, then there is absolutely no way to make this graph colorable or color this graph. Okay? So if all 3 of them are false, then there is no way to bring anything other than F here. This will always be F, which is bad, right? Cool. Are we good? Can anyone figure out number of nodes and edges in this construction? So we have done the reduction. We have proved that we have reduced 3 set to 3 color. But we have to show that it took us polynomial amount of time to construct this graph, right? So if the original formula has n n variables and m clauses. Can someone tell me what's the number of nodes and edges in this graph? Quick math. क्या?
क्वेश्चन था ये हमने all तो कर दिया but like how are we going to AND it with other clauses?
So we do this for every clause, okay? Which means that for every clause we are making sure that the output cannot be an F. So the AND is by default. So I'll have a similar structure for the second clause and the third clause, and for each one of them I am connecting their output to F, like this. Okay? So over here I'm doing kind of an AND. If I connect two nodes by an edge, that's an AND by default, right? I'm making sure that they don't receive the same color. Okay? Quickly, not exactly, but a rough estimate of number of nodes in this graph in terms of number of vertices and clauses. So let's do a calculation. So for each clause I have 3, 9. Okay, so ये वाली जो 3 vertices है ये वहाँ से आ रही हैं. Okay, so I don't have to count them. 6 vertices here per class. So I have 6 times how many? 6 times something जो अभी मुझे आपने बताना है vertices यहाँ पे. उसके बाद I have 2 times something here plus 3. This is the number of vertices in my graph. अब यहाँ पे you have to fill in the blanks. उसके बाद edges हमने count करने हैं. Edges में you have 3, 6, 7, 8, 9, 10, 11 times something plus 3 times something plus 3, I think. Okay, time to fill in blanks. 6 times. Yeah. And 2 times number of vertices, and 11 times. So 3, 6, 7, 8, 9, 10, 11. 11 times, yeah. 11 times m and 3 times n for each of the variables, plus 3 for the edges in the triangle. So that's not bad, right? It's linear in the input size, which is polynomial. Okay, the graph is not that big. So we can definitely construct it in polynomial time. All right? Okay. Running out of time. Any questions? Yes? No? No? Okay. Let's quickly go through the slides then. All right, so you create a palette triangle, the one over there. You create variable gadgets, which is that you connect each variable to its negation, and you connect both of them to the base color. And then you construct this clause gadget, which is this, जो यहाँ पे है, which is kind of a conjunction of 2 triangles. So this structure mimics the OR operation. This is the correctness thing. And here is kind of a proof that if everything is F, then you can't receive anything other than F there, which means that this gadget is not colorable. If the first one is true, the other 2 are F, then there is a way to receive a true color at the end of this gadget. If the third one is true and the first two are false, then you can do the same. If all three of them are true, then you can receive the true color too. That's that. Here's kind of what it looks like for the complete formula. Okay? So you get these gadgets for each of the clauses, and then you connect them with the variable gadgets and the palette triangle. This, along with the first thing that you proved with, which is that 3 colorability is NP, proves that 3 colorability is NP complete. There are a couple of remarks regarding K-colorability. So if I ask you to check whether a graph is 2 colorable or not, this is easily doable in polynomial time. This is same as checking whether a graph is bipartite or not. Okay? And you did that, I think, in one of the homeworks or in the first exam. Oh, was it the first exam? Worksheet. Okay. Okay. So that's that. The last part is, I think, something that you can do on your own. So this thing proves that 3 colorability is NP hard. What about 4 colorability? Is it NP hard? This is kind of an easy thing to do. I think it's a 5 to 10 minutes exercise. If you understand ये वाला proof, अगर आप understand करते हैं तो I think you should be able to reduce K colorability to 3 colorability. Okay? So if I give you input as a graph of K colorability problem, input as a graph for 3 colorability problem and reduce it to K colorability problem. Okay? So right. So there are 2 steps. One, if the original graph is 3 colorable, the new graph should be K colorable. If the original graph is not 3 colorable, the new graph should not be 3 colorable. One of these statements is kind of super easy to do, trivial. The second is the one that's going to take 5 minutes, I guess. Yeah.
Can you also prove K-colorability is NP hard by reducing it to a K-satisfiability problem?
Right. Yeah, you can do that. You can reduce K-sat to K colorability. थोड़ी सी यही वाली construction है, but instead of triangles, you will have slightly larger structures. So palette जो triangle है ना, palette triangle will become a K-clique. Right? A K-clique is a complete graph on K vertices as a subset in a different graph. Yeah.
How would the reverse reduction
Proving reducing 3 colorability to 3 sat, वो obvious नहीं है. That requires, I mean, it's not obvious at all. क्यों?
So it's not like reverse of
No, it's not. It's not. क्यों? It's not. Because remember, अब आपके पास जो input है, it's an input of a 3 colorability, which means that you can have all kind of messy graphs as input. You have to figure out a formula which matches those graphs, right? यहाँ पे बहुत nice structure था ना. We constructed a graph which is super simple, nice. Triangles हैं और कुछ भी नहीं है यहाँ पे, right? But in general, graphs could be super messy, irregular, right? So it's not easy. It's not easy at all. Okay. All right, I'll try to prepare a homework for reductions, but that won't be a graded homework. It would be a bunch of practice questions, but they'll help you for the exam. Okay. So look out for that. Thank you. We meet on Monday.